Okay, ladies and gentlemen, a couple of perfunctory things to kick right off the bat. If you are interested in the local tsunami outreach program, a number of you went by the table as you were walking in. Feel free to take a moment. Lindsay and Michael will be out there in the lobby afterwards as well. And also, you might have seen the Sunset Preparedness Fair. That's going to be taking place on April 14th. So if part of the reason you're here is the quake tsunami thing and thinking about getting prepared, that's something that you can take advantage of as well. Also, there are these lovely handy-dandy little geology lecture series flyer things, because how many of you think that this talk is actually taking place this evening, right now, and also tomorrow evening at 7 o'clock in the Hale Center? Well, it is in the paper that way, but guess what? If you're planning to come for part 2, please don't. You will come here, and there will be a nice, lovely cutout of Dr. Weldon that says, sorry, we tried to alert people that this was not the case. So anyway, it's not tomorrow, but you can be prepared for the next 3. And also, if you got a place to post, Dr. David Montgomery from UW is going to be coming down talking about landscape change, and the effects on salmon here at February 25th. And so if you got places to post these, I'd be glad to have you take them and post them so that I don't have to. And also, if you didn't sign the sheet, yes, pieces of paper for one geology instructor. If you didn't sign the sheet, please take a moment on the way out. One of the things being able to bring these for free is trying to prove that people actually do attend. Cat hop. Anyway, people do show up, and we can't prove that if we don't have some indication that you actually are here. So this is kind of one of the ways that we do that. Too much stuff. So this evening, it's my great pleasure to introduce to you Dr. Ray Weldon. And Ray did his undergraduate work at Pomona College and did his graduate work at Cal Institute of Technology. He's worked for USGS and also for JPL, Jet Propulsion Lab. Yeah, several people are currently turning their electronic devices off. If you have an electronic device that's currently on, would you please turn it off? Thank you. Thank you for the reminder, dear lady. He's also presently the department head at U of O and has come over here to discuss with us this evening both distant as well as some local implications of earthquakes and tsunamis. It's my pleasure to introduce to you this evening Dr. Ray Weldon.
Thank you, Ron. And I'm sort of stunned at the size of this room and the number of people here. I'm really honored to have so many people spend their Friday evening with me. I really appreciate that. What I want to do today is to talk a little bit about the earthquake and tsunami in Japan, but talk a lot more about Cascadia. And the particular theme I want to focus on today is, what does it tell us about Cascadia? Because in Cascadia, we have all kinds of models. I'm sure, as many of you know, there are models that say the tsunami will be either 30 feet high or 100 feet high in some models. We have models that say the shaking will last a minute or 2 minutes, or it'll exceed 1 gravity in terms of the measurement of shaking. And how do we know that? I mean, are we just making this up and trying to scare people? And so the real thing I want to focus on today is to try to educate you a little bit. I'm sorry, I am a professor. And I want to educate you a little bit about what we do know about Cascadia and show you how we can use other examples like the earthquake tsunami sequence in Japan to test our models and essentially vindicate the models, or say, well, they're too big or they're too little or whatever. You know, these lights are really bright. Is it possible to make them a bit lower? Or I'll live with it, I guess. Okay. So this is one of my favorite pictures of the tsunami coming in here. There are lots and lots of great pictures of the tsunami and the earthquake shaking damage. you know, there were these giant whirlpools with boats in them, damaged nuclear power plants, these incredible scenes of the water coming into these towns in Japan. And that's not really what I'm going to talk about tonight. So sorry about that. There's wonderful videos and movies and pictures on the web. I'll show some more, don't worry. But that isn't really, this isn't sort of the death and destruction that we're going to flip through here. What I really want to do is educate you a little bit about what we know and what we think will happen in the future. So I hope this is a review for most of you on the coast here, but just in case it isn't, I'm sure as many of you know, we have a plate, the Wanda Fuca plate. It's sort of a shell on the surface of the Earth subducting underneath us here, underneath North America, shown schematically here. And it's really this interface between the two plates that generates these very, very large magnitude earthquakes. Now, I just want to remind you that there are other sources of earthquakes. There are earthquakes that occur in the downgoing slab as it bends. These include the Nisqually earthquake recently, the Olympia, Seattle earthquakes that some of you may know about. And then there are crustal earthquakes formed by little faults or flaws within the crust as well. Many of you probably felt the one near Woodburn or the Klamath Falls quakes. But today we're really going to focus on the subduction zone interface, especially out here on the coast. That's really what matters. Now, this is a great graphic, and this is from an article called Cascadia from National Geographic, and since they can draw a whole lot better than I can, I like using some of their pictures to explain what's happening here. Some of you who have National Geographic may have noticed that the February issue, the current issue that just came out, is also about this topic. I see some head shaking. It's really quite good. This one in Cascadia is a bit dated, but it's really pretty good. So let me just go through it here for you. What happens here is essentially we're on the leading edge, this triangular edge of North America here. Let's see if this one's a little brighter. There we go. This triangular edge here, and the oceanic plate is pushing against it, as you can see in this pretty picture here. And so you can imagine if we had the ability to measure the distance between the coast and the interior here, we would see the coast moving towards the interior between earthquakes, and we can. We can see that clearly with GPS. Also, as this wedge gets compressed in here, it bows up. See how this little thing shows it bowing up? And so the land would be rising between earthquakes. And then in the earthquake, effectively when this gets so stressed that it slips out, this part of the land will jump out. And of course, as it uncompresses this wedge, it will cause it to drop. And so if we're coming to the coast here, what happens here is, remember, this toe of North America gets pushed out. And the way I want you to think about this is think of like a big shovel. Imagine we have a big shovel upside down under the water, and if you were to push that shovel out, of course, it's going to lift the water that's above it, as shown really nicely in this little cartoon here. Well, if you lift a whole bunch of water up, it's got to go somewhere, right? So it flows away from this uplifted area and forms the tsunami. Now, at the coast here, the ground goes down. And so as shown in this cartoon, the ground goes down, the tsunami comes in because the uplifted water runs across the ground here, but the ground doesn't come back up so that the water is permanently higher. And so we'll come back to these, but I like to do a little demonstration here to sort of get people to really visualize what's happening. So my left arm here is the downgoing plate. My right arm here is North America here. Sorry, try to talk to the microphone here. So here's this wedge I'm talking about. Some people shake their hands. They see where the wedge is, heads. It moves like an inchworm. So think of an inchworm. So I'm pushing on it. This goes up. Then the inchworm goes, and then I push on it, and it goes up, and the inchworm goes up. We got it here? Just think inchworm. We all know how an inchworm moves. Okay, that's how I want you to be thinking about this process between and during earthquakes. Okay, the rest of it, you can go to sleep now. I've taught you what I want you to know, but there's a lot of details that I want to fill in a bit here. Now, as I said, this is like a theory, okay? And we want to, first of all, explain to you how we developed this theory, and then we want to show you how we can test whether it's any good or not when we actually have an earthquake. So the earliest evidence, and again, I'm sure you've heard much of this, are these ghost forests that are in the coast. So this is a salt marsh here. These are salt-tolerant grasses here. These are red cedar here. These were drowned in 1700. I'll tell you how we know that in just a second, because they are now below high tide and they don't like being in salt water effectively. If we look at an exposure in a sea cliff or in some place where we can see this, we can see the old salt marsh level here. We can see tsunami sands on top of it, and then muds again, and then the marsh again. So this grass here is this grass that if you were to dig a hole and look at it, you would see a sequence like this. So geologists cut into these trees and used tree ring dating and radiocarbon dating to show that they were drowned in the winter of 1699 to 1700. And what they found is all the way from Humboldt Bay through the whole Oregon coast up into Washington, perhaps even as far as Vancouver Island, all these ghost forests had the exact same age. Okay, so that suggests that something catastrophic happened at about the same time. Okay, now, again, if we were to look more carefully at this, for example, here's a place actually in Washington from Brian Atwater's work. This is a sand dune site. This is old ground surface here. This surface was actually occupied by Native Americans. You can see some fire pits here. On top of it, we can see the tsunami sand from 1700, and then the tidal mud. Because remember our inchworm analogy, between earthquakes, or during the earthquake, the ground drops, right? So what was above water is now below water, and we're depositing the tidal mud here. Now again, how do we know that? I mean, like I said, did some crazy geologist just make this up? Well, again, you can go to places where this has happened, and a good place is in Chile, where in 1960 we had the largest earthquake tsunami sequence in the past sort of 150 years. And again, you see the topsoil, you see the tsunami sand, you see the tidal, you know, the intertidal muds, and then the grass occupying it. So this is sort of like a signature that you can see that tells you, and of course in 1960 we know that happened because people were grazing cows on that surface there before the earthquake and tsunami, and then they went there afterwards, and so we know exactly what happened in this particular case. Okay, so moving to more recent ones, this is the tsunami from Sumatra in Thailand. I actually have two sisters who live in Thailand, so I go there quite often. And Thailand, of course, was struck by the tsunami that was generated in December 26, 2004 from the Sumatran earthquake. This is a picture here of some people fleeing for their lives, but of course their mother coming out to rescue them. They actually lived, fortunately. And people in Thailand said, this is something that's unprecedented. This never happened before. How could we know that this would happen? And of course, all we needed to do was dig some holes in the ground here, and we see that this has happened repeatedly. You can see this is the tsunami sand from 2004. There's the old tidal marsh. There's a previous tsunami sand. There's a tidal marsh. There's a previous sand. There's et cetera down the way. These have all been dated with radiocarbons, so we know this happens about every 600 to 700 years at this spot. And at low tide in the sea cliffs here, you can see the exact same thing. Okay, so it shouldn't have been unexpected. It should have been known that this would happen. It's just, you know, people's memories are short. The people living there didn't remember what had happened 600 to 700 years ago, and thus they said, wow, this is something that we can't imagine to have happened, but clearly, if you're a geologist, you realize you could. Okay. The other piece I want to touch on here are the Native American oral traditions, because they're very useful. Some of you are probably familiar with some of this, but just to give you some examples here. These are some quotes I've taken out of various publications where these oral traditions have been written down. So for example, this one is interesting. they had practically no way or time to try to save themselves. I think it was at nighttime. Nighttime is a theme that comes up a lot, and I'll focus on that more in the talk here, okay? I think a big wave smashed into the beach. These people were lost, but these other people, I won't try to pronounce that, who translates to house up against a hill, the wave did not reach because they were on high ground. So these records actually tell us that people who were living really close to the water, you know, were inundated by the tsunami in 1700. The people that were living higher up, such as these people who lived up on this hill, were not. And that becomes very useful information to say things about how big the tsunami was, because these people lived and these other people didn't, for example. And to show you the other kinds of things we learn, another thing that's really common in these are these landmark rocks, okay? A lot of these tell myths about the Thunderbirds struggling with some bad whales, and then they landed on the ground, and then they turned into rocks. And this is something that puzzled people for many years until Sumatra occurred. And so let me show you how this was figured out. Here's a picture from the Sumatran tsunami. This is a small peninsula in Indonesia. You can see the city here. It was completely devastated during the tsunami. What I want you to focus on is notice that there's all this sand along the edges here, and then look up here now, there's all these gullies and rills, and the beaches are all gone. Well, what happened is, you know, we all think about the water coming in, but the water got to go back out too. And as the water goes back out, it really erodes and strips out a lot of the sand and vegetation. And you can see this on the ground here, okay? This is actually a person for scale back in here. There was a hotel here. This is a major highway here that was destroyed. And before the tsunami, the trees came right down to the high water mark. So the tsunami just stripped off all the vegetation and all the sand here and exposed these rocks. So now let's think about our coast here. There's lots of sand on the coast. Imagine the tsunami comes in, rips a lot of the sand off. What are you going to see? You're going to see some big whale-shaped rocks, right? Because those rocks are sitting there underneath the sand. It's just buried by the sand, and it just stripped it away. So the Native Americans get up the next morning after being shook around, and they look out there and go, wow, look at this. You know, there was a beach here, and now there's a bunch of these big rounded rocks. You see the point that I'm making here? So again, scientists had no clue about this, you know, until actually seeing a tsunami, seeing it happen, and now we can make better use of these oral traditions and better understand that we can't just worry about the tsunami coming in, we got to worry about the water going back out and what it's going to take with it. Okay, so getting back to this, I just wanted to remind you of this picture again. So again, what happens is we compress this area here, it jumps out, lifts up the water, makes our tsunami. Now we have models about this, and the models of course then turn into how high the tsunami is going to be, where it's going to be worse. It also, these models tell us how long the shaking will last, how great the shaking will be on the coast versus the interior I-5 corridor and things like that. So let's just see, in Japan, did this happen? I mean, you know, to what extent are these predictions vindicated by what happened in Japan? So I want you to remember, think about this inchworm, as I talked about, with this wedge of North America jumping out towards the ocean. And that's exactly what we saw happen. So just to show you what we're looking at here, this is Japan, northern Japan here. All these little red arrows here are geodetic monuments that actually had GPS sites on them. And you can see the epicenter of the earthquake, and then the rupture zone was here. You can see by the way these arrows are pointed here and how long they are that basically the edge of Japan literally leapt out, and you probably remember hearing in the news and such that, you know, the margin of Japan moved like 40 feet or something towards the US and things like that. Well, this is exactly what happened here. So remember my little inchworm here, we're pushing on this like this, and then it went jump, just like we think it did. And because Japan has got this remarkable network of GPS monuments, we can actually see it jump out towards the ocean. Similarly, we can measure how the ground goes down. Remember, the other part of our little inchworm here is as this gets compressed, see my knuckles, when it jumps forward, my knuckles come down, and that causes the ground to drop. And that's exactly what you see. All these vectors are showing how the ground went down. So now we can say, okay, this isn't just some nightmare that a geologist made up. We've actually got instruments that were sitting there when the earthquake happened, and we can see exactly what the earth did. Okay, so again, we can talk about this tsunami. Once again, what happened is near the coast, the ground goes down. Out here, the ground goes up and outward, as shown by this arrow. And basically, it uplifted all this water. It dropped all this water down, and the wave came in. Waves came in. Just to give you a sense of what this looked like, you can see here are places along the coast where measurements of the water height was made, and these are in meters. Yes, meters, okay? And the highest was like 40 meters. That's like 130 feet, okay? And so you can see in the area here where the ground leapt out the most, the tsunami was much higher. In the areas here and here where the ground didn't leap out quite as much, you can see there was a significant tsunami, but not anywhere nearly as high. So it tells us what we had thought all along. If you have a lot of locking, or in other words, that inchworm is really tightly locked to the plate here, when it jumps a lot, and the amount that jumps, of course, tells you how big of a tsunami you're going to have. Okay, so just a few more things on the tsunami here. This is a great figure here. It basically shows how the waves were pushed out across the Pacific Ocean here. We, of course, received damage up here in Oregon, but it was really largely directed towards South America here. The colors show the height here. But even here on our coast, we had substantial damage, as you all know. And I put this up here because I didn't rush out to the coast and watch it. I actually listened to the emergency managers and stayed in Eugene. It was hard to do that, but I did, okay? I turned on the computer, however, and was looking at all the webcams I could find and the tidal gauges. This is a tidal gauge from Port Orford here, as I recall. This is the usual tides, and this has the tides subtracted out, and you can see the waves going through here. And even as far away as the Oregon coast, the largest swing of water was almost 8 feet, and it swung from high to low in about 20 minutes. And so there's really a dramatic effect even this far away. And of course, this is Crescent City showing some of the damage. Now, the other point I want to make is from tsunami like this, we can say how long it takes to get to different places. This is going to become important in a moment, okay? So we can tell from looking at these tsunamis and making models about how tsunamis propagate across the ocean basin. We can say, for example, that it took something like 9 hours or 10 hours, more like 10 hours to get to Oregon, and we can also look at other tsunamis and see how long they take to get across the ocean. Okay. So one more thing on tsunami, we're almost back to Oregon here, is in Japan they have a really good written record, and they distinguish in Japan between tsunamis that are local, i.e. they're associated with earthquakes. The Japanese well know that when you have a large earthquake on the coast, you're likely to be followed by a tsunami. But they also have what they call orphan tsunamis. And these are tsunamis that are not associated with the earthquake, so they've properly inferred that this means that they came from somewhere else. And this is some of the evidence from the tsunami in the winter of 1700 here. And I just want to point out a couple of things. For example, that that this tsunami lasted like 18 hours. So this ship that you've been reading about here, went out on the open ocean. In the open ocean, the tsunami went right past the ship. It had no clue it was there because out in the open ocean, even though there's a meter or several meters of elevation, it's spread over hundreds of kilometers, so you don't notice it go by in the deep ocean. And then when they tried to come into the bay, the water was sloshing in and out of the bay for so long that they couldn't get in there. Other issues are, how high the water was and things like that. So we use this information from Japan to tell us about the tsunami that was generated here. And then, so this is a little simulation to show what it looks like. It'll run twice, or I could run it a few more times, but why don't we watch it? And then these are the hours up here at the top, so watch it again. It's propagating out. It's going across Japan here, and then you can see even 18, 17 hours later, the whole Pacific Basin is still quite agitated, okay? So again, let's see if we can go back and forward to make it happen again. So a few features. We know from the records in Japan that it swept down the coast from north to south. Okay, we know something about how high the water was at different places, and we know something about how long the water remained too agitated for the boats to get in and out of the harbors. Do you see how we can use that information, plus information and models of how the tsunami tracks across the ocean basin, to essentially take the information in Japan and say something about what happened here? And so what we've learned from that is that between 9 and 10 p.m., January 26th, this was last night, okay? I think that's why this talk is today approximately, okay? In 1700, we know that we had a magnitude 9 earthquake. And we know it's a magnitude 9 earthquake, not an 8, not an 8.5. We know it's a 9 based on the height of the tsunami and the duration of the tsunami in the Pacific Basin. So we can use this information from Japan to basically say something about that there. So you can see they sent us a tsunami last year. We sent them a tsunami in 1700, and we'll keep sending them back and forth for the foreseeable future. If I go back one more time, and then we'll move forward, you can see we're pointed at them. So they got it a lot worse. Remember, the tsunami last year from Japan was pointed down towards South America. So we're getting the better end of this exchange. Okay. The other point that I want to come back to, as I did in Japan, there was a lot of discussion in the media about how this was unexpected, that we couldn't have anticipated this event, that there's no way we could have known this would happen. This was particularly pushed by the people who own the nuclear power plant when it was found that their tsunami walls were too small. They were going, there's no way we could have known this would happen, okay? And the point, this was published in American Scientific Journal. I want to show you some others. But it was quite well known that there had been similar large tsunamis in this area. Just to show you one paper, okay? I can't read the date up there, but can you guys, it's like 2001 or something, okay? There's this earthquake or tsunami called the Shogun tsunami, which is very similar to the one that occurred. It occurred in 869 here. This had been published. There were 5 or 6 papers in the Japanese literature. There are multiple papers in the English literature, including this one here. Geologists were well aware of this. In fact, Rob Witter, one of my ex-students who I think has talked to you here, who used to work for Dogami, gave me these pictures. He went there. These are exposures here. Here's the tsunami deposit here on top of the old salt marsh, as we saw before. It's overlain by pieces of volcanic tephra. There was an eruption of several volcanoes right after the tsunami, so they know the age of this. And so it's well known in the geologic literature that in 869 there was a tsunami. It was comparable in size and extent to the tsunami that occurred here. Once again, most people don't think on geological timescales. 869 is a long time away, a long time ago. And just as as in the case in Thailand that I mentioned, people forget, they, especially without written records, people forget that these things happen, even though there are written records of this as well. Okay, back to Japan. Back to our interface. Now, I hope this picture is familiar to you by now. We've got this wedge of North America that's overlying and being, pushed above, or the Juan de Fuca plates pushed in. And so now I want to show you the kind of data that we're using to actually make these models that will tell us, how big the tsunami will be and how much shaking there'll be and how long the shaking will last. Okay? This is more for a talk in the I-5 corridor. I'll just go through it quickly. What is this? Is a prediction of ground motion or how much shaking there'll be. I'll come back to this later if people are interested. But just to say, if you take two competing models for the shaking, I just want you to notice, this is the I-5 corridor here. You're right at sort of the boundary between the red and the yellow here, which is basically at the boundary of where you start seeing significant damage. If you were to take this other model that suggests that the area of locking, or this piece of this wedge of North America that's being compressed, is much smaller than that, you can see that the I-5 corridor in particular, here's the bend in the river, so Portland's here, Eugene is here somewhere, is actually outside the area of significant damage. I just think you should notice here's Coos Bay here, you guys are in the red area no matter what. So this is maybe a bit academic for the people that live here, but for people like me who live in Eugene, it really does matter whether there's just sort of 50 kilometers or so of this pointy wedge, leading wedge of North America that's being compressed like a giant spring, or whether there's 100. You guys are on top of it. You guys are going to feel a lot of shaking in either case, and we can come back to the shaking later in the talk if you wish. Okay, now, how do we know how much shaking? How do we tell an engineer who built the bridge across the bay, for example, that it's going to shake, for a particular period of time, or it's going to shake in particular frequencies, or it's going to have a certain amount of acceleration, which is usually how we measure shaking. Again, these are just models, okay, until we actually have an earthquake. So again, Japan is absolutely wonderful because it has a really dense network of seismometers here that measure the ground shaking. And what we're seeing here, and the details don't matter, is the amount of shaking. Again, the sort of yellow color is where you start to see significant damage. Red is where you have, a lot of damage no matter what, and blue is less. You can see by focus on this one in particular, you can see this strip of red along the coast, yellow inside going back to about Tokyo, which is in here, and then the rest is here. So what we can do is we can now say with real data, not just a model, not something that we run on a computer, but with real data that we can measure what the level of ground shaking will be. And frankly, it's a bit alarming. Here's just an example where you can see greater than 1G. 1G is, once you have shaking for a minute or two at 1G, only the very best built structures are going to survive intact, okay? So anyway, the point that I want to make, the theme here, this isn't to alarm anyone, okay, but the theme that I want to make here is that now we have a data set to test and refine our models and make better predictions of what the ground motion will be when it happens. Okay, now, remember our little cartoon, and this is more like the inchworm. We all see the inchworm here, okay, good, okay. It's getting ready to jump forward. And so we can look at the uplift that occurs along the coast, and it should have the shape that I'm showing in a more formal manner here of what the uplift will look like. And just in very simple terms, the peak in uplift is more or less above the down dip extent of the lock zone, okay? So we have an area that's fully locked, okay? So this triangular part here is fully locked onto here. And you can see the peak of the uplift is a little bit beyond where it's fully locked, just like this picture. So this motivates going to the coast and seeing if we can measure this pattern of uplift. And that's what my students and I do. And I'm going to focus on that for a few minutes. Okay? Now, the easiest way to measure this uplift is with sea level. okay? So first of all, I think you all know a little bit about sea level. You have a great tide gauge that measures sea level at Charleston there. But just to show like a San Francisco and Seattle record, these are places that are away from areas that are being uplifted, like our coast. We'll come back to that in a moment, okay? You can see that water is rising, okay? Just to diverge for a moment here, global change is real. The Earth is warming. Sea level is rising, largely because of heating up of the ocean. You can see sea level is really rising here. These little bumps you see here are El Nino, La Nina cycles in here, which are shared amongst the whole ocean basin. But if you go to the Oregon coast, or the Washington coast in this case, and look at Nia Bay, you see the same pattern, like see this big El Nino in 84, 85 here, you can see up here as well. But it looks like the coast is going, that the water is going down. Why is the water going down? The coast is going up, okay? So if you know what the rate of sea level rise is, and over this time period it's about 2.3 millimeters a year, in round numbers, 1/10 of an inch per year, okay? You can say what the ground has got to be doing to defeat it. Does everyone see the point there? So the reason much of the Oregon coast, in particular Washington coast as well, water's going down, isn't that sea level's going down, it's the land is going up faster. So we can just subtract that from sea level and get an idea of how fast the ground is going up. That seems complicated from here, but I hope you got it. Okay, there are details in terms of sea level isn't rising uniformly all over the world. In fact, there are some places where the ocean is going down. This is because the warming of the ocean is not uniform. There's also changes in currents. There's changes in salinity and other things that matter. But in the Oregon area, we know what sea level's doing. It's going up about 2 to 2.5 millimeters a year. Okay, so we've installed tide gauges all over the coast. There are wonderful tide gauges like the one at Charleston here, but there's lots of places without them. So some of the things that my students do is actually install tide gauges, and you can see we're having fun here. This is in the context of one of my classes that I teach. And so here's a tide gauge being established in the Siuslaw River near Florence, near Cushman here. And looking at historical records, this is from the 30s. We had a great recession or depression, whatever you call them, back in the 30s too. The government decided to spend money instead of not spending money in that recession, and one of the make-work projects was to put tide gauges in every harbor around the U.S., so we have actual tide gauge data all over the U.S. coast from the 30s. That's where that data is from. This is from the 70s when NOAA came in to measure water level for a dredging project. And then this is 6 months of our data that we collected here. And you can see a very clear trend. Okay? Now, remember, sea level is rising at 2.3 millimeters a year, but we only see 1.4 millimeters a year of sea level rise here. What does this tell us about the uplift of the ground? Some quick math here. Good, 0.8 millimeters a year of uplift at this spot. See, it's really that simple. Okay, the other piece of this that we use, I'm almost done with the boring part. I can say I'm losing some people, but I'm talking about my data and my students' data, and you're going to have to listen to it for a little bit, okay? Then we'll get back to the fun stuff. Okay. The other data that we use are releveling lines. So in this area, these data that I'm showing here are actually releveling in the I-5 corridor and on the north flank of the Olympic. But we've done this as well here. For example, many of you are familiar with the railroad line that runs from here to Eugene. That was put in 1914. They leveled it when they put it in. It was releveled in the 30s by the NGS. Pieces of it were releveled off and on. Beyond that, my students and I have releveled the part from Mapleton to Cushman in the Siuslaw Valley. I'd love to relevel part of it in this part of the world. I hope the people from the port are here. You were invited, please. In any case, the point is that what happens is, since the ground lifts more by the coast than the interior, it produces a tilt. So you could imagine if you leveled from Eugene to the coast in 1914, as they did to build the railroad, okay, and then you re-level that again, and if the coast is going up, you should see a tilt. Does everyone see sort of the point of the re-leveling? And this just shows some examples. If you go from Nia Bay inland, you can see very high rates of uplift, like 3 or 4 millimeters a year, and it decreases monotonically. And you can see it agrees perfectly with the tide gauges. So these little yellow stars here are our estimates of uplift based on the tide gauges that I just showed you. And then if you look at the leveling data, it matches that perfectly as it does in the I-5 corridor. These are tide gauges, these are re-leveling. So what we do is we assemble all of this data, and we now have, based on a lot of student work, basically, a complete record of what the uplift is in all of these places where you see these little dots. Okay, so every little one of these little points here are places where we've measured the uplift rate, and you can see there's a lot of them in there. And remember our shape that we're expecting to see. You can see that shape in many of these figures here. Okay? We model this. Okay? So what we do is we take our model and we say, okay, how big is the inchworm? Is it an inch or an inch and a half? Okay, to follow that analogy up. In other words, is only a little tiny piece of this wedge being compressed, or is a big part of this wedge being compressed? And that's what we're really trying to figure out here. And that's what we've done here. So we make a model. Okay, so all these data points with their error bars are data that my students and I have pulled together. The red points is the model that fits the data, and you can see it fits pretty well here. And then what we're looking at here is our model of what we call the lock zone. In other words, what portion of this leading edge of North America is actually locked. And you can see there are some significant differences up and down the coast if you're squinting hard to see. I think with my eyes, I think that we're right in here, right? I think I'm pointing it near Coos Bay in here, okay? What we see is a very wide lock zone up by Astoria and up into Washington here. It narrows and narrows, so it's actually quite narrow in this area here. It dramatically increases in the Bandon area. Sorry, I heard some people were here from Bandon, okay? The lock part is much wider here in the Bandon area. And so effectively now we can say, okay, now we know what part of the subduction interface is locked so that we can actually start to figure out, you know, how much is it going to jump out when the earthquake occurs, how close to the portion of that interface that's slipping is, say, Eugene or Coos Bay or whatever. So that will tell us how hard the shaking will be. And the width of this is proportional to how long the shaking will be. And of course, that tells us how big the tsunami will be by over what area is pushed out to lift the water. So you can think of, for example, in the Astoria area, that's a really big shovel that's being pushed under the water and lifting it up. But in the Newport area, it's a pretty small or relatively smaller shovel that's pushed under the water. Okay, we tracking here? We're getting there. Okay, good. People are still with me. Okay. Now, just a couple of final points here, and then we can answer some questions. Again, some more from this Cascadia article in National Geographic. Also, February of this year's National Geographic has a lot of this. This is actually Florence here with this black line. You can't read this. I got it off the web. It's not very good. This is the 101 bridge here. This is downtown Florence, but you guys have seen these inundation maps. They exist for this area as well. The thing that a couple of things that I want to point out, and I can answer questions about these later, is that in Oregon, unlike many places, we've actually moved forward based on scientific knowledge, and as you guys know, there's lots of tsunami warning signs, there's evacuation routes and other things like that. There are inundation maps. Again, this isn't a very good one, but it was handy when I talked about this. And the point that I want to make is that this has been moved forward simply on the basis of geologists and other scientists looking at the evidence, reasoning logically, drawing analogies with other places. And I'd like to say this is very different than many places, okay? When I first came to Oregon and started teaching at the University of Oregon 25 plus years ago now, people did not believe this story, okay? And even in the absence of an actual earthquake, the building codes have been revised. There's been a focus on, warning people about tsunamis, and a lot of effort that many of you are aware of, just based on the scientific knowledge. Again, this is really different than other places. For example, California, where I grew up academically, it wasn't until the big Long Beach earthquake in 1933 that destroyed a lot of schools, killed a lot of school children, led to the Field Act, which required that schools be built better. It wasn't until after the Silmar San Fernando earthquake in '71 where they invented the Acquas-Prioli zones, where you can't build on an earthquake because on a fault zone, because there were hospitals and freeways that were destroyed because they were right on fault zones. Every single case where things have actually changed in California, it's been following an earthquake. Okay? And so what I really want to emphasize here is that in Oregon, we've made tremendous progress in terms of mitigating this future hazard here just on the basis of scientific evidence. We haven't had to have a disaster to do this. So from my perspective, that's tremendously positive. Okay, some conclusion points here. Okay, again, we did have a magnitude 9 earthquake off the Oregon coast. There's really no doubt about that. Nobody doubts that. It's scientific, accepted scientific fact now. Okay? It generated a tsunami very similar to these tsunamis that we've seen recently, and I showed you how we can figure that out based on what's happened in other parts of the world. The part I was talking about, strain, or this compression, it's like squeezing a spring, if you will, this compression or strain is building up. We can see it, okay? We can see it with our tide gauges and our releveling, and we know that this locked area that we've identified is consistent with another magnitude 9 event coming up. And based on the intervals between them, which we can calculate either by looking at prehistoric events or by looking at how fast this strain is accumulating, that these events have about a 0.3 to 2% probability per year. So kind of in round numbers, it's about 1% per year probability. Depends a lot about your probability model, and we could talk about those details if you want. Now, not something to be overly alarmed about, frankly. I feel like it's very unlikely I will see this event at my age, but some of the kids in this room will. Okay, you multiply 1% times 30 or 40 years, then you have a pretty good chance of seeing this event. Okay, which means we need to start preparing for this event. We need to start knowing what we're going to do, building our schools and critical structures in a way that it will survive this event. Okay. Again, that's not an alarming number. I just drove here from Eugene. The odds of doing that every day for a lifetime is much higher of something bad happening. Okay. And again, the kind of work that my students and I are doing here at the University of Oregon or in Oregon is to basically try to actually collect data in Oregon so that instead of just having a model that is just based on theory, we have real hard data, and we're applying it to models that have been tested in the real world in places like Japan to actually tell us exactly what will happen. Thank you very much.
Hello. So this will be a little bit difficult with all of you, but we'll take a few questions. We'll pause for a little bit and then probably sit in here for those of you that have some additional questions. So I need to have you speak into this for the questions because we're web streaming it and also archiving it as well.
That sudden spread about Cape Blanco in the size of the zone, is that caused by the Klamath Mountains, perhaps?
So the question was that dramatic widening as you go south, essentially in the Bandon area there. what causes that, and is that possibly because of the presence of the Klamath Mountain terrain? And that's one idea. There's a major boundary in the architecture of the crust. Basically, north of there, you're sitting on an accreted piece of oceanic crust called Silesia. Geologists in here might be familiar with that term. South of that, you're on Klamath Mountain crust, so it could be the change in the crust there. Another theory is, for those of you who know the distribution of the plates offshore, there's also the Blanco fracture zone that separates the Gorda plate from the Juan de Fuca plate. If you project that onshore, it's about the same place. So there's a couple of different hypotheses for why that's there.
So you mentioned that driving out from Eugene, it's not a big deal, and you don't think this is likely to happen while you and I are still alive. However, what if it happens while we're sitting here? I mean, have you any way of at this point, gauging how much the buildup it is and and when it will release? Yeah. Any gauge at all?
Yeah. So the question is, basically, is there any information available out there that tells us, how close we are to this in terms of how much strain is accumulated? Or whatever else effectively. And the short answer to that is actually no. So what we do know is that we can look back in the past and look at how often these earthquakes have occurred in the past and look at the intervals of time between them. We can also look at how much strain was released during these earthquakes and say how much is enough. And it turns out it's pretty variable. So there are intervals of time that are almost 1,000 years long where we haven't had one. And then there are other intervals of time where in 1,000 years we've had 3 or 4 of these. So they're really quite irregular. Now, before we get too carried away with saying, well, it's totally random, there are potential precursory phenomenon that occur. So for example, in Tohoku, for the example, a week before, in fact, can we advance the slides? I don't have the control. Is there someone up there who can go to the end of my talk? I have a slide for this, and I didn't plant this guy. But let's go to the end of the talk here. Go up one, up again. Oh, darn. Okay, we'll leave that one for a moment. But I thought I had a slide. I didn't bring it with me. But there was a magnitude 7, I forget, 4 or 5 days, almost a week before, and there were other foreshocks. So in round numbers, somewhere around 10% of large earthquakes have what are called foreshocks. And so Japan should have probably paid a little more attention when a magnitude 7.2 happened in this area, and then when it was followed by a whole bunch of 5s and 6s and 4s. So, for example, if we had a 7 offshore here, and then it was followed by 4s and 5s and stuff, I think that there would be a lot of alarm raised. So there's some chance, it only happens in like maybe 10% of them, that there will be something obvious like foreshocks. Another thing that happens is that the inchworm doesn't go all at once. It sort of would start creeping a little bit and then go. And so in many earthquakes where there's good instrumentation, there might be some perceptible movement occurring, right before the earthquake. So presumably, and this is something that's a hot area of research, is that if we have lots of GPS monitors or tide gauges or whatever we're using to monitor the deformation, and we watch them in real time, we might see some changes in these rates of strain accumulation, some accelerated strain release. Another thing that happens are these things called slow earthquakes. Maybe some of you have heard about those. My students and I are working on those. There are slow earthquakes that occur, essentially earthquakes that last like for weeks, so you don't feel the shaking. The shaking is on a very long period that we can't sense, but instruments can. And so I think there's some optimism that there will be some sort of precursory activity that we might interpret, okay? I would say, however, the odds are good that we will have no warning and that all we can do is say what is the probability during a period of time. That's a really lot of words to say no, wasn't it?
A lot of us are really interested in the inundation zone maps, especially the updated ones that Dogami was going to put out back in October. And I heard from a scientist from locally here that they came out a day or two ago. So this is really unfair to you. Have you been able to see any of the new inundation zone maps, and can you describe one to us maybe?
Well, I would encourage you to go to their websites and look at them. One of the issues that was motivated by that second to last slide, and I had some other slides that I could have shown. Another thing that we've been doing with these tide gauges in the Siuslaw drainage is at one time we had up to 6 tide gauges. We had one out on the Spits and the open ocean. Then we had several near town, and then Cushman and Mapleton, etc. And one of the things we're interested in is how the water will propagate up into the estuaries, because you guys don't live on the ocean. And in Oregon, most people don't live on the ocean. You live in estuaries and in bays, such as we are here. And so the major criticism I have of a lot of these inundation maps is that they're really based on what's going to happen out on the open ocean, and the amount of science that goes into what happens as this water propagates into the bays and estuaries is not really well known or applied. So just to expand on that, you probably have noticed if you look at the tidal range at Coos Bay, for example, and compare it to the tidal range at Empire or Charleston or out the ocean, it's different, right? Must be some fishermen here that have noticed that. Come on, I'm not the only person who's noticed that. Okay, well, take my word for it. In the Siuslaw, where I'm much more familiar with it, okay, certain periods of waves get damped down as they come into the estuary. Other periods of waves, due to the bathymetry and the shape of the bay, get amplified. So, for example, in the Siuslaw, waves of the period of tsunami waves will be amplified about 20%, for example. So the point I was going to show with some slides but can't is that if you really want to get detailed understanding of what the inundation is going to be like here, one, you need a more detailed model like the one I showed. The models that the current inundation maps are based on are scenario models, not based on real data, but hypothetical earthquakes. So that's a problem to start with. And then there isn't a lot, they work really hard to figure out what the water level is going to be at the coast, but your house isn't on the coast, right? It's in the bay. And so I think there needs to be a lot more effort to make these models of how the bay is going to respond to the water coming in, inform those models by actual tide gauge observations. It's something we've worked at because there have been a lot of tide gauges here in the past. There was one in Empire for many years. There was one at the docks here for a while. And I think you could build a model that would much more accurately show what the inundation is. Having said all that, the fact is, for all of you sitting in this room, when you feel that earthquake, and you're not going to miss it, you don't need alarms to tell you something happened. When a magnitude 9 earthquake happens on Cascadia, you're going to know about it, I assure you, okay? After you pick yourself up off the ground, and the shaking literally will be on the order of 2 minutes, and you probably will be on the ground, you want to get, 100 plus feet up, okay? Fortunately, in a community like this, you don't have to go really far to get 100 feet up. It isn't like Thailand, where my sister lives, where it's 20 kilometers to 100 feet up, So, we're really lucky in the sense here that we have a coast with a lot of relief. And rather than worrying about whether Dougami's right about it being 30 feet or 50 feet, I wouldn't stop at 40, I'd get up to at least 100 and make sure that I'm up there.
The slide that you have up here, it appears that the really big earthquakes seem to be clustered around 1960 and again around 2010. Is there any theory or data to show that these big earthquakes do occur in clusters?
Yeah, and I'd intended to draw up another slide, but I brought this slide because almost always someone asks that question. They always say, well, wait, there's Sumatra, and then there's Japan, and there's all these earthquakes happening. So I did put this up to show that. As the person who asked the question noted, during the 60s here, we had Chile, which you could see is monstrous. I mean, Chile was like a 9.6 or something. You know, that's just a whole different beast than anything we've seen in the instrumental. This is essentially the well-instrumented record. And there was, you know, the Good Friday earthquake, 1964. Some of you might remember there was a tsunami here, caused a lot of damage in Crescent City, killed some people on the Oregon coast. And then, obviously, we've had this cluster recently. People who do statistical analyses of this argue that that's no different than pulling from a random distribution. So just like you can go to Las Vegas and, you know, win at the table 3 times in a row, on average, the statistics are going to work out. And so there really is, this is not statistically different than, you know, drawing from a random distribution.
So, ladies and gentlemen, I'd like to first thank the tech support crew, because 2 of the 3 guys came up from Brookings this afternoon, where they christened the new Curry campus a little bit earlier today. I'd also like to just take a second that I didn't thank earlier, Oregon Resources, for financial support for the lecture series so we can put this on for free, as well as the College Foundation and the Community College for providing said tech support all the way from Brookings, most of them, on a round trip, as well as this wonderful hall, and all of you for showing up this evening for the 7th annual Cascadia anniversary talk. Also, just pencil in February 25th if you're interested in salmon and landscapes. We've got Dave Montgomery here. April 20th, which is a Friday, Peter Ruggiero from Oregon State is going to be coming here talking about different styles of coastal hazards. And as Ray Weldon mentioned this evening with sea level change, Dr. Julianne Struve on the 19th of May is going to be talking about sea level change. She's coming to us from Boulder, Colorado. So thank you very much, Ray, for making the trip over to the coast tonight. And I know he'll be more than happy to continue answering some questions. If there's a whole bunch of you, we'll leave you sit here and we'll just keep the discussion going for a brief period of time. Otherwise, thanks for coming out and have a wonderful weekend.